Hi everyone, my name is Mr Ogretme, Head of Physics and Joint Head of Science at Newstead School. This is a nice opportunity for me to say welcome to studying physics at Newstead School. This gentleman is Richard Feynman, one of my heroes in the area of physics. He used to say that the physics is the pleasure of finding things out. So throughout your studies, I would like you to keep in your mind this phrase, the pleasure of finding things out. Yes, we're going to have exams in front of us and we will be assessed, but more than that, when you study physics, hopefully we're going to share the pleasure of finding things out in the universe and everything in this beautiful world surrounding us. For example, if you just look at this, it looks like to me one of the images from a microscope, but this is actually a representation of some data and how we can use that data in quantum computing. So physics is one of the main areas, main pillars of quantum computing studies. On the other hand, you may have heard something like this. This is the colorful pattern from a film, a thin film, like a soap film or an oil film. You may have seen one of those things on the tarmac after a rainy day. If an oil droplet from a vehicle lands on the water on the tarmac and is creating those colorful patterns, and how do they happen? Physics can explain those type of things, and actually in today's lesson we're going to look at taste the lesson. We're going to look at waves. You already know a lot about waves, but I would like to show you how it is slightly different in A level compared to GCSE. So we human beings here to understand from the very small to very big. So what are we made up of? Cells? Well, cells are made up of atoms. What is inside an atom? What is it that makes up those protons, neutrons? Do we have smaller things inside electrons? Where are they? Is electron really a fundamental particle? Where did we come from? Is the universe, does it ever end? Are there other universes? Big questions. Big questions need big thinkers, big ambitions. So that's you guys. You may have seen this image before. This is Curiosity, right now exploring the Mars. Thanks to physics, an amazing piece of gadget. Do you like science? Yep, it began with physics. You want skills? Yep, we learn them as we study physics. Do you want a job? You are more likely to be hired if you studied physics. Do you like money? What beats other sciences? Physics. Well, talking about money, I need to show you this graph. This is average graduate salaries. So as you can see, physics in the top 10. Studying A-level physics is going to give you a taste of how it would be like studying physical sciences, engineering, or pure physics at university. First of all, it's an amazing journey. You will learn lots of things. The way you think, the way you look at the world is going to change. But the most important thing for you that even just only A-level physics in your CV is a great plus. It's going to give you an edge. And if you have a physics degree, there are lots of things that you can do in your professional life. Here are just a few examples of them. Environment and climate, space, energy sector, medicine, education, just like me as a teacher. There are lots of other things that you can do. I'm just trying to show some of them here. What can I do with a physics degree? Well, there are some really nice videos
on that web page. Have a look, I highly recommend. And also wanted to share those 2 slow motion videos with you, 2 of my favorites. I wish I could say I video recorded them, but no. I really like slow motion videos. They really do help us understand things around us. About 30 years ago, we relied on ground-based observations. Like we could only see the galaxies, the events that took place about 6 billion years after the Big Bang. When we got the Hubble Deep Field image from Hubble Space Telescope in 1995, it was a big leap for us because we could see the galaxies which were there in about 1.5 billion years after the Big Bang. And then we got ultra deep fields in 2004, and it was wow moment because we could see the galaxies about 1 billion years old after the Big Bang. And in 2010 we got Hubble ultra deep field taken by infrared imaging. So that was even much better than ultra deep field, and because we could see the galaxies which were there, which got formed about 500 million years after the Big Bang. And the future, well, James Webb Space Telescope is coming, and we should be able to see even further back in time, and that is so amazing.
This is your telescope, an engineering marvel, an exploration powerhouse. Use it to look back in time and explore the first galaxies that formed after the Big Bang. To peer into atmospheres of planets orbiting the stars. It's your eyepiece to the uncharted, unknown, and unimagined. This is the largest, most complex, and challenging space telescope ever constructed. It will change our understanding of the universe and our place in it. The James Webb Space Telescope. Equipped with the largest primary mirror ever to be flown in space, at 6.5 meters, it's more than 6 times the size of the Hubble Space Telescope primary mirror. Webb's 4 cutting-edge infrared instruments and cameras operate at super cold temperatures. Temperatures colder than the surface of Pluto. Getting this cold is done with the help of the largest sun shield ever flown, a 5-layer, tennis court-sized sun shield that blocks heat from the sun, earth, and moon. Webb will be the first telescope to detect light from the most distant galaxies in the universe. These first galaxies formed about 13.5 billion years ago, only 300 or so million years after the Big Bang. Webb carries advanced technologies to tackle some of the most fundamental questions about the universe. How did the first galaxies form and evolve? Are there chemical signatures of the building blocks of life on other worlds? Is our solar system unique? Launching such a large telescope into space is an incredible engineering challenge. Fully deployed, Webb is too large to fit inside any rocket fairing. Engineers designed it to be folded, like origami, to squeeze inside the European Space Agency's 5-meter diameter Ariane 5 rocket fairing. After launch, controllers on the ground deploy Webb remotely. Deployment is an intricate ballet. For nearly 3 weeks, controllers carefully unfold Webb. After this delicate dance, Webb's golden mirrors are precisely aligned using motors behind each hexagonal mirror segment, adjusting them to form one perfect mirror. Once the instruments are fully cooled, the exploration will begin. Webb is a technological challenge like no other, born of the efforts of thousands of people across the United States, Canada, and Europe. The James Webb Space Telescope is your telescope. Use it to explore, to challenge theories, to see sights yet unseen. It's yours to unfold the beauty and mystery in the universe and our place in it.
Independent learning, it is a big part of A-level physics. On average, you would need about 4 hours of extra time on top of your timetable lessons. It is going to make a big difference. If you rely on your timetable lessons only for your physics studies, you may end up with not getting the best out of your potential. So that's a pre-warning for you. Now, into today's taster lesson. We will be looking at waves, but how did we come to that point? You studied motion, how things move around us. You looked at the forces and how it affects the motion as well. And then we looked at the energy. And the final, the next step in our studies would be waves, the wave model. So it will explain how certain phenomena around us is taking place, our understanding of waves. In a general sense, anything that moves back and forth, to and fro, side to side, in and out, or up and down is vibrating. A vibration is a periodic wiggle in time. A periodic wiggle in both space and time is a wave. The world is full of waves: sound waves, waves on a string, seismic waves, and electromagnetic waves such as visible light, radio waves, television signals, and X-rays. All these waves have as their source a vibrating object. Here you can see some animations of a pulse. Here we go, this is a pulse, and that's a special type of pulse, and here is another special type of pulse. If you have a train of pulses, you have the wave. For a wave to happen, for a wave to take place, you need a vibrating object. Here comes our first definition, a progressive wave. Progressive wave is an organized disturbance with a well-defined speed. In our lessons, the must-have knowledge, the things that you really do have to know, will be presented to you clearly with an orange box and an orange outline. So there is no way but you have to make a note of them. Please pay attention to a single point on a string at rest, highlighted by a red dot. When the disturbance travels through the string, the red point only goes up and down. However, we see the disturbance in the simplified shape of a sine curve traveling through the medium. The graph on the left at the bottom shows the displacement of the red point from the equilibrium position with respect to time. The second graph shows how the disturbance looks at an instant, for example at the 27th second, a snapshot of it. There are two features common to all waves. A wave is a traveling disturbance. This is something common in every wave. We have a traveling disturbance. And also waves carry energy. A wave carries energy from point A to point B. This animation shows how a particle in the medium displays a cyclic motion. The medium here in this animation is the blue string, an ideal and elastic string, and we are only focusing on two particles on it, shown by a red dot. Starting from being at equilibrium point, in the first quarter of the full cycle, the particle moves upwards to its positive maximum displacement in 5 seconds. Then in the next 5 seconds, the particle comes back to its equilibrium position. Now half a cycle is complete. In the next quarter, the particle keeps moving downwards to its maximum negative displacement. From the 15th second to the 20th second, the particle moves from its maximum negative displacement to the equilibrium point.
That was one cycle completed. The bottom picture shows one full waveform. That's what we call waveform, that shape, that sinusoidal shape. Pay attention to the difference between the way particles oscillate and the way the disturbance, i.e. the wave, moves. The black arrows are showing the velocity vector at that instant for that particle in the medium. As you can see, it's continuously changing. The blue arrow is showing the velocity of the wave, which is constant from left to right at a constant speed. Now I would like to introduce you one of the amazing websites about physics simulations. This is called PHET, or PHET, done by University of Colorado in States. If you Google PHET, it will directly get you there. You will see lots of simulations, not only in physics, in other disciplines as well. So please go and have a look and play with those simulations. They are really good fun, and if you like computer games, like me, they are really good fun. You can create lots of amazing things with them. Waves can be put into two main groups, mechanical and electromagnetic. Propagation means the transmission of energy in a particular direction or through a medium. The main difference between these two types of waves is that mechanical waves require a medium to propagate, and electromagnetic waves do not require a medium to propagate. However, remember that electromagnetic waves can travel through matter. That is how visible light can go through glass, for example. Electromagnetic waves simply do not need a medium to propagate. You are familiar with lots of electromagnetic waves. Some of them are visible, some of them are not. So, like for example, this remote control uses infrared to communicate between the handset and the device, such as telly. Like when I press any one of those buttons, you can see that it is giving out infrared, and the camera in my laptop can detect the infrared, but when you do it to your eyes, you can't detect it, you can't see it. Try it at home. Another interesting thing is not every digital camera can detect this. The camera on my laptop can, but the camera on my iPhone does not, because Apple products, they have a very strong infrared filter in their camera. So let me try to demonstrate this. So now you can see the screen of this camera on. So what I'm gonna try to do, here we go, like I'm gonna, so just a minute, here we go. Right, here we go. So you see the light picked, the infrared picked by my laptop, but you don't see it on the iPhone camera, which is strange at first. But we know that the iPhone camera has a very strong infrared filter, which blocks the infrared coming from there. It's basically just proving that there is light that we cannot see. Show this to your mum or dad or brother or sister tonight. Both in a pulse and in a progressive wave, the hand transfers energy to the string, and that energy is transported down the string and can be transferred to an object at the other end. All forms of progressive wave transport energy. A pulse is produced by a hand holding the end of a string and moving up and down once. The wave pulse moves to the right. The key difference here is the difference between the velocity of the particle and the velocity of the wave. Alongside the grouping as mechanical and electromagnetic, it is also possible to put the waves into two simple sets, transverse and longitudinal. The slow motion video shows a longitudinal wave on a slinky. Before you move on to the coming slides, you may like to think about the difference between a transverse wave and a longitudinal wave by just looking at those animations on the video. I don't know you guys, but I really like slinkies. They're not very expensive. Go and buy one, and they're like Science Museum sells a really nice, cool one, metal one, the best. And we use them at school as well to demonstrate waves. Now here we have a train of pulses creating waves on the slinky. If you don't have a slinky, you can create waves on a tight string as well. An elastic string would work better. But it is possible to create another type of disturbance in that elastic material, in this case the slinky, and it is basically you move your hand backward and forward quickly, and you create a compressed region, and that region would travel. So that is a longitudinal wave. If you keep doing it, rather than creating a longitudinal pulse, you would create a longitudinal wave. This is an important part of our lesson today. Please make sure you grasp the difference between transverse and longitudinal waves. For a mechanical wave, a transverse wave is a wave in which the particles in the medium oscillate perpendicular to the direction in which the wave travels. I say it for a mechanical wave because that definition is slightly different for an electromagnetic wave, which is also a transverse wave. So the direction of energy transfer is perpendicular to the direction of the particle's vibration. So here I have the direction of energy transfer from left to right, and the particles vibrating up and down. So please pay attention to the arrow that I have used for the particle vibration. I have used a double-headed arrow to show that they're going up and down, up and down, up and down in this example. In a longitudinal wave, the particles in the medium oscillate parallel to the direction in which the wave travels. So here I am showing those directions with arrows. Please do not say particles move up and down and wave goes to the left for a transverse wave. And please do not say particles go to and fro and wave goes forward for a longitudinal wave. Such descriptions are not valid and will not get you the full mark in an exam, maybe no marks at all. Stick with the description that you see here. Make a note of them. Orange. So here we have animation where we have the particles and also a longitudinal wave. The small red dot represents one of many particles in the medium through which a longitudinal wave propagates. If you focus on the compressed regions, you will see they move from left to right. But if you focus on one of the red particles, you see that they oscillate around the fixed point. I'll leave it for a while for you to have a look and to get hypnotized. Well, now this slide brings us to the end, and I would like to give you a summary. So what's a progressive wave? An organized disturbance that travels with a well-defined wave speed. What's a wave? Well, a wave is an organized disturbance that travels with a well-defined wave speed. The reason why we say progressive waves is because there are some other waves as well which we do not study in A-levels, but that's the definition that you need to know, progressive wave. And all waves do carry energy. It is possible to put the waves into two groups, mechanical and electromagnetic. Mechanical waves do need a medium to propagate. Electromagnetic waves do not need a medium to propagate. And there are two types of waves, transverse and longitudinal, and the difference between them is basically focused on the difference between the way particles move and the way energy travels. As long as you know that difference, you're done. Great, thank you very much for your time, for the tester lesson on physics, and I really do look forward to seeing you all back in September. Have a lovely day.
How do you do, ladies and gentlemen?